podcast about this 30 years later about where I specifically disappeared to.
On this singular day of complex analysis. In case you know in the reporting.
Two things. So if I haven't got your homework from last week, get that to me today. Are there questions on the homework that's due Wednesday?
Not
before we talk about stuff from the reading.
I did like what? Tell me. Because I don't think the problems require any of the stuff I asked you to read.
Okay.
I might be wrong. Let's. So.
Can we talk about the circle and radius of convergence?
I do hope.
Oh, then there it does.
Okay.
There we go. Yes, we can. Absolutely.
Also, we should turn on the lights.
Okay. Or open the blinds. Okay.
No, just open the blinds. Oh! What was that?
Next one.
Ooh!
No, I like Olivia's idea a lot better.
What was? Yeah. Let's try that.
That's better.
Oh, that's lovely.
I like natural.
Gosh, I was blind.
Thank you. That was terrible. That was just.
Good job,
Thank
Olivia.
you, Olivia.
So slow clap. Yeah. Let's talk about circle of convergence. So, quick review. I will be reviewing some things, Sydney, so do not fret, my friend. We are talking about infinite series, and I've got a beautiful pen.
Yeah, that's a good one.
Yeah, it is. Primo. So an infinite series is just an infinite sum. This classic move is to confuse series and sequence. The good news is they're actually just the same. It's just a slightly different tweak on sequence when we talk about a series. So an infinite series is an infinite sum. When we don't usually say the infinite part on series, probably just call them series, but things only get interesting once we actually head out to infinity. Quick fun fact, hey, what does that add up to? It's one of the most baffling things in all of mathematics, perhaps.
0.
No.
No,
Good guess.
it's 1 over.
It's negative 1 over 12.
It's negative 112.
Oh yeah, we did this in real analysis.
Yeah, I hated the day we did that.
What?
Did you?
That broke
Yeah.
everything
Oh,
in my.
so
I hated that.
so let's talk about
It's only that if you assume a lot of things.
a lot of things.
A
Like
lot.
my whole
Yes.
math career.
Yeah. So it's disturbing. So this was. Do you remember who actually demonstrated this? If he told you that, we have a problem. Unless his middle name is Ramanujan.
See, I don't remember that name.
He didn't mention that?
I remember.
I don't remember.
I just
that
remember
name.
this from Calc 2. I don't remember.
Yeah, this is the kind of thing I like to pop out whenever I have a chance. But Ramanujan was a self-taught mathematician in India. And he was working with series on his own. He was just teaching himself and doing all this work, and he started corresponding with this mathematician Hardy in the United States, or the UK. What?
I thought it was UK.
Yeah, I think it's probably UK. It's probably UK. And he was just doing stuff just like without fear. The kind of fear that is produced and the kind of boundaries we set on ourselves when we look at that and you say, well, everything here is positive, everything here is a whole number. If I stop this at any point along the way, it's an integer, a positive integer. It's increasing. How on earth could I get this? So I'm not going to spend time in class like proving it. Some of you have seen it. You can find the proof online. Look up negative 1/12 and don't go to Reddit to find out about it because that's a shit show.
What?
That is such a fun place.
Yeah, it can be. So this is super counterintuitive. However, there is also a thing called the Riemann zeta function. So that just seems like madness. But you can demonstrate it if you naively proceed and you forget about things like converging sequences, converging series. The Riemann zeta function, of which I make t-shirts out of and stuff like that, the Riemann zeta function actually can be used to show that this is true. So Ramanujan proved this naively. The Riemann zeta function actually verifies. The Riemann zeta function looks like this. So let's see. I don't know what zeta looks like. That's a pretty bad zeta. It's a half-assed zeta. You know.
I think it's beautiful.
Well, thank you.
I don't know what zeta looks like.
That's lovely. So the Riemann's, there's many forms of it, but we have this kind of primal form that looks like this. But S can be a complex number. So S is this is one of the most famous complex functions. One of the great outstanding problems of this is the Riemann hypothesis that is escaping me right now, but it's about the zeros. When does this thing equal zero? And it's about the nature of the zeros. I think it's, does a zero exist in some particular region? It's unsolved. This is an unsolved problem. But this thing here, notice that the zeta function of -1 is actually probably needs to start at 1, actually. Is really just that series up above. And using other forms of this, there's an integral form of this thing. If you plug in -1 into the other form, you get -1/12. So Ramanujan uncovered this secret, strange fact about the world that doesn't make any sense. And it, like Noah said, it makes sense, but you have to make a lot of weird assumptions. And honestly, I don't even know what those assumptions are.
One is the series that like oscillate. Their sum is just the midpoint that they oscillate around.
Yeah, so if you do the 1 minus 1 plus 1
Yeah.
minus 1, that's a half, right? That's
Mhm.
kind of what he worked on that. Yo, I see what you're saying in terms of,
Yeah.
I guess I was like thinking of assumptions about the world, how it works. But that's a pretty good one. That's a pretty good one. I guess it is the same. We come to the same place.
I would just like to point out that I really thought you were going to say ramen noodles every time you said his name.
I used to say Ramanujan, and then a Hindu friend of mine said, no, it's Ramanujan. And so I was like, okay, yeah, you're the Hindu English teacher. She helps people learn both. So anyway, an infinite series is just an infinite sum, but it's also a sequence in a way. It's the limit of a sequence. The way we understand an infinite series is through partial sums. So the first partial sum is just the first term. The second partial sum is the sum of the first two terms, and on down the line, just inductively proceeding forward. So when we talk about this is actually the limit of the partial sums as n goes to infinity. So to understand a series, we convert it to a sequence of values. This is just a list of numbers, and we think about, does this limit of this sequence converge? So if this thing converges, which we generally write as minus infinity if we weren't in the complex plane, but in the complex plane, infinity is a much more interesting thing. So if this converges, then we say this is the sum of the series. And if it doesn't, we just say it diverges. In the complex plane, we know that convergence is all like a much more complicated thing as well, right? You can converge to a value in lots of different ways. So let's take a look at one of the most fundamental kind of series that is going to become one of your best friends this rest of the semester in the precious time that we have left. Let's just talk about geometric series. What's a geometric series?
Good question.
Thanks.
It's a series where every term is multiplied. To get from term n to term n plus 1, you multiply by a common factor.
Well said, well said. So a geometric series starts off with some number. Now this is going to be a complex number for us. And to get to the next term, just like Noah said, I multiply by a common ratio, r, and get to the next term. And then I multiply that by r, and I add on the result. And so I get this thing that's just really just a sum of different powers of r multiplied potentially by some starting number a. So that's a geometric series. This is an infinite geometric series. Let me first make it finite so we can see something here. So let's look at this thing as though it stops at the n minus first power. How many terms are there? So the terms are the things that get added. How many things are being added there? N. So n things. So this is the nth partial sum. This is a good little derivation you should be somewhat ready to do, not for me, but as a mathematician, a person who understands this is how we get to understand geometric series. So, what if I take the nth partial sum and I multiply by r? And here r is a non-zero complex number. And this is the subtraction sign, so I'm taking complexes minus 0. What am I going to get? Well, I'm going to get AR. So this A times R gets me AR. Notice I'm leaving a little space here. Plus AR squared. So I take this times R, I get that. This times R, I get this. And I go down, and eventually, when I take the term right in front of this one, it's going to have n minus 2 as the exponent. So when I multiply by r, it'll look just like that. And then when I take this times r, get that. So I just multiplied the terms by r. And it shifts them in some ways, right? It kind of shifts them to the right. So then we make a line because we're going to subtract. Because look what would happen if I subtracted. So much stuff would cancel. Seems like a fun thing to see no matter what we're doing. You know, just trying things out. So nth partial sum minus r times the nth partial sum is the a lasts, everything else cancels. And then down here I've got nothing for this power, so it's minus a to the r, a times r to the n. We're starting to get a nice formula. So now on the left I've got this. I can factor the s sub n out. Over here I can factor the a out. And I can divide by 1 minus r, and I actually have a nice closed form now for the nth partial sum. So that's pretty cool, because then I could do all sorts of neat things. There's no restrictions on what r can be, except that r shouldn't be what. So the only thing r can't be is 1 when we make this move from here to here. What if r was 1? What if r was 1? What's the sum?
NA.
It's just n copies of A added together, yeah. So if R equals 1, it's just A plus A plus A, n times, just get NA. We don't need formulas to do that. We can work that out easily. So I've got this nth partial sum right here. So if I want to understand this, infinite sum, it's going to equal the limit of that formula, which is limit as n goes to infinity of, let's just write the formula down again. There's only one moving piece in this whole thing, and it's that exponent on the r. Everything else is a constant. So we want one little result here that I'm going to kind of try to roughly argue through, and hopefully you'll believe me. But the limit, I think we can argue this pretty well, of r to the n is going to equal, we've got a couple options. First off, let's just think, what if r is a number of modulus less than 1? So r is somewhere in here. So in other words, r equals some rho e to the I theta. And what do I know about rho? It's a real number with absolute value, what? Less than 1. So when I take r to the n, it's going to be rho to the n, e to the I n theta. Okay, just multiply the argument by n. What happens to this rho to the n? So this thing here, this just bounces around. This is just multiplying, moving multiples of theta. So the second power is 2 theta, third power is 3 theta, and I just kind of keep spinning around. This just rotates me. What happens to rho as n goes to infinity? It goes to 0. Because this is a fraction, right? So a number that's less than 1 is just a fraction of something. It's like a fifth or 3/4 or something like that. You keep taking a fraction of a fraction of a fraction, you get to 0 eventually. So what I'm trying to say, I was just trying to argue roughly there, that the limit of r to the n for a complex r is 0 if the modulus of r is less than 1. Here's a more interesting question. What if r equals 1 and I'm on that circle? What could I say about this limit? So now let's just say modulus of r equals 1. It's literally on the unit circle. What happens to powers of it?
They stay on the unit circle.
They stay on the unit circle because the modulus is 1, and so powers of 1 are 1. But what happens to the point? What would the motion picture be? So here's just the point. Here's r. What happens to r squared? Moves, right? We just move around the unit circle. So it just kind of rotates around. It might hit the same spots if we're lucky. It might never hit the same spots if r is weird and irrational. It might never come back to where it started. You might just see, you could think of its orbit as all the places it hits. But it lives on the unit circle. That isn't convergence. It doesn't settle down. So it diverges if r equals 1. Unless r is just 1, and then we're okay. If r is just 1, we're good to go. But we're not gonna worry about that, because this is the case we're mostly interested in right here. And then it's certainly, what happens if I'm out here? What happens if r is out here? What do powers of r look like? What's the movie?
I'm just gonna kind of shoot out and go around the circle.
Gonna rotate, spin out. Remember, think about the Mandelbrot set that we were talking about, how some of those points rocketed off to infinity in a spirally way. Right? Because powers just keep you rotating, and then they also grow you if you're already bigger than 1. So this is divergent. How about we just say greater than or equal right there. Cool. So now we actually understand everything we need to know to get this limit. So what is that limit equal to, assuming the modulus of r is less than 1? What does this become? Top is definitely A, and then the bottom, we still have that on the bottom.
Oh, yeah.
Yeah, that's cool. You had the right idea. This piece dies off. The only moving piece dies off if r is less than 1 in modulus. So here's our formula. I can say now that if I have an infinite geometric series, I know everything about it. I own geometric series. You own them. Now, so if we have this, like, yeah, what were you saying, Noah?
I like owning things.
Yeah, it's the American way.
Yeah, one of these days I'll own property, maybe.
I hope so. I hope you do.
It's more likely I'll inherit property.
Every other generation has made that very challenging for you.
Yeah.
So I hope that you do. If modulus of r is less than 1. So let's take a look at some examples. What does this series do? First thing you check is, what is r? What is the thing that I multiply from term to term? What is that common ratio? What is its modulus?
Square root 2 over 2. No. Yeah, it's just square root 2.
It's this point right here. That's r. And what the modulus is square root of 2. So what does this series do? Diverges. I'm done. Awesome. So here, this diverges. Let's get used to writing some things. Diverges because we have a geometric series with r equals 1 minus I, and the modulus of r is greater than 1. It's low-hanging fruit. It's not super satisfying, but it knocks it out. It's the truth. It's all we can do, unless we're Ramanujan. Now you got me, damn it.
Ramen noodles.
Let's go, oh my God.
Yeah, it's fine.
I will never hear that the same way again.
You can't tell me I'm the first person to hear that guy's name.
It's literally the first time I've ever heard that, so thank you. I will never forget you or that. I would have remembered you anyway, but now.
Oh no, you're just like a goldfish with most people. You instantly leave this college. We're dead to you.
Oh, look at that. Ooh, getting crazy. Got a new index. Ooh, let's make it 1 there. Let's do this one together, because I want to point out a couple easy ways to get a handle on this. I would actually write out a few terms. I probably should have done it over there. It never hurts. But it's nice to understand what you've got, especially when this index is starting somewhere out further. So this is 3, 2 over 1 plus 2i to the first. And of course, using just pedagogical psychology, you probably know this will converge, because you've been at school and you know how to play school.
Wow. I've never had a teacher use that word or assume I know how to play school before.
That's what we do. That we are all academics, we know how to play school.
Wow.
Yeah.
Wow, 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 wow.
The game of school. So, look over here. What is A? A is the first term in the series. So sometimes I write this formula like this. It's the first term over 1 minus the common ratio. That's a real easy way to think about things. That means this is A. What is R? What is it? What do you multiply?
That was the-
What do I multiply by to get from here to here?
2 over 1 plus 2i.
So keep an eye, and sometimes that's not obvious. Now, Sydney, to get from this term to this term, what do you multiply this by to get to here? And it's just another one of these dudes right here. Does that make sense? Yeah. Sometimes that, and really, I highly recommend thinking about it this way because it's not always super obvious. Sometimes the powers don't just go up by 1. So that's why I think this is a good way to approach it. Does this converge, and if so, to what? Answer is yes, but show it, and then give me the sum, please, while I eat a piece of candy. Getting 2/5 for that modulus. We know we're good because that's less than 1, so we can proceed. Yes.
What did we do over?
Square root of 5. Thank you. Good, solid. Thank you. I was thinking, what is she gonna ask? What's wrong up there? Good call. Thank you. Thank you, Bill. Is this less than 1 though?
No.
What's the square root of 5-ish?
2 plus something.
2 point something.
It's the square root of 20 over 25, so it is less than 1.
Yes,
If you want
yes,
to
yeah, I
calculate
like that.
a
That's
different
cool.
way.
That's a good idea. Yeah.
What? Rabina, you have to speak to me. You can't whisper to me, I can't hear you from over there.
She's using the shiny.
Oh. Are we talking about the movie or the Pokemon?
I don't know anything about Pokemon.
Okay,
So
so the
movie.
movie.
Yeah. So the horror film.
Yeah.
That's what I'm. So root 5 is like 2.36. So this is definitely less than 1, albeit just a little. So then just go to the sum. First term over 1 minus common ratio and simplify. So notice these little words that I'm writing. This is when I'm saying to you, add stuff that if I've written on your paper, write more. This is the kind of thing I'm asking you to do. Noah writes
Yeah, I was gonna say.
more. I've never written that on your paper. That's for sure.
Not familiar with that term.
That makes sense.
Right, more.
Yeah, no. No, you write opuses, opi. I don't know what the plural of opus is, but you have written it. So it converges to, and then we just go to the formula. First term is that weird 6 over 1 plus 2i. 1 minus 2 plus 2i. What's the easiest way to simplify that?
I simplified the fraction earlier because I didn't want to have to
Yeah, I think there's an easier route.
We could just multiply everything by 1 plus 2.
Yeah, let's just multiply through by the denominator, the common denominator. And so then that just becomes, multiply top and bottom by 1 plus 2i. Make sure to keep your parentheses and stuff around. See how nice that is. So that's 6 over negative 1 plus 2i. And you know I wouldn't want you to leave it there. So we multiply by the conjugate. And we get negative 6 minus 12i over literally the modulus of this thing squared. So that there's that 5 I was looking for earlier. So my final answer is negative 6/5 minus 12/5i. Not remotely obvious. Not to me. Yeah, there's this famous quote. I forget who wrote it. It was some physicist, like Lord Kelvin or somebody like that. Somebody who was called a lord, for God's sakes. It's a statement that says something like, I think that said, he says, to a mathematician, this is obvious. Louisville was a mathematician. That was his quote. So I've always told myself, well, I guess I'm not a mathematician, because that ain't obvious to me.
Ah.
Yeah. So let's take this problem a little bit bigger and then answer the question you're wondering about, which is the circle of convergence. We're going to start off a little bit chill. For what z in the complex plane does the series sum from 0 to infinity of z minus I to the k converge? So now I've got a variable in there. Now I've got this letter in here, and so the series value changes depending on what z is. So notice here. Z is variable. What's the lowest hanging fruit value that converges for? Yeah, right, if z is I. Sweet. If z equals I, what? Well, that series, I'm a little worried about the 0 to the 0th beginning, but I think that thing just converges to 1. Because this, what I would do is I would write this out like this. This is z minus I to the 0, which is 1. I'm going to just call it 1 before I plug in the z and cause trouble. But it looks like this. So that's what that series looks like. This is a power series. And a power series means any series that depends upon a variable and can change value depending upon that variable. In general, a power series looks like this. It's got coefficients times z minus some point c to the nth power. And we can start this at 0 without really getting anything, without being wrong, ever. So this thing right here, this is called the center. This number here, c, is the center. And c is a complex number for us. These are the coefficients. And really this thing is just an infinite polynomial written in a very specific form. So this is a power series. We want to answer that question up there. Here it's pretty, life is cake, because we have a geometric series in particular. So notice that this thing is geometric. This does not have to be. Why? why does this not have to be? It can be. What would make this not a geometric series? Let's write it out, because it looks like this. What would make this not geometric? Can you give me an example of one? That'd be cool. Or were you gonna say something, Lavina? Sorry.
I mean, the z minus c being multiplied is making it geometric.
No, if the A's aren't constant.
Yeah, so that's it. So we gotta keep these A's, or the A's could be multiples of something and multiplying. But if, so for example, Lavina, let me show you what I mean. You're definitely, you're onto it. But what if I had a series that looked like this? Oh, here, let's just do. This isn't geometric, because to get from here to here, I multiply by 2 times z minus I. But to get from here to here, what do I multiply by?
3/2.
Yeah, 3 over 2 z minus I. And then to get from here to here, I multiply by 4 over 3 z minus I. So it's not a common ratio. No common ratio. But the good news is, that's not what's happening yet. We're gonna have an easy way to deal with all these, but I wanna relate what we just talked about to the question at hand first. So you have a couple ways to get there and understand what we're really doing. Let's do it. And I probably should have summed up what the picture looked like from the last one, but it's a little late. So let's just take this thing. This is definitely geometric. A, the first term is 1. The common ratio is z minus I. So I'm just noting the rhythms here. That's what we do. We're mathematicians. Mathematicians just catch rhythms and do stuff with them, exploit the rhythms. When will this converge? So this converges if what? That's what it would converge to. Let's just write the condition out, right? That's when it converges. Yeah, that was I was just looking for something a little simpler. So this converges if this, i.e., well, I actually know what R is, if that's the case. What does this look like? What is this shape? If I plot all the z in the complex plane that make this true, what am I plotting?
A circle.
Circle. Where's the center?
Open.
Open circle, open disk.
Disk. Yeah.
Open disk, because the circle's the edge, right? But we have an open disk. Where's the center? I. So the center's right here.
And the radius is 1.
And the radius is 1. Exactly. So this goes up to 2i up here, and it goes out to 1 plus I. So right over here, it's 1. That's minus 1 over there. And it converges for every z inside there. That's the disk of convergence. So we have a center at I, and the disk of convergence, I don't know, I'm gonna be a rebel and spell that like that, of convergence is right here. I never know if it's C or K. I don't think I've ever actually spelled it like a discotheque, which is a really old person word to know. Let me give you one. Actually, let's just move on and then we'll just work some together. I kind of want to just get it so we can do anything and then have fun. So in a geometric series, life is pretty simple. You're really hoping for this. If we don't have a geometric series, as in that example I had earlier, which I might want to pop up here. So what about this series? Sum k equals 1 to infinity, negative 1 to the k, over k times 2 to the k, times z minus 1 minus I to the kth power.
For the last problem
Yes, ma'am.
over there.
Yes.
So would our answer just be the picture and say that the shaded area is our disk of convergence?
Yes. This also, so you could say disk of convergence is this, and here's the picture.
Okay.
Yeah.
I feel like there's this theorem that says for any alternating, this is an alternating series that is getting smaller, presumably.
So we don't have alternating series anymore.
We don't.
Does that make sense?
Yeah, that does make sense. It does make sense that when it would only be something when you had a real number line that there was
Exactly.
two halves of.
Yeah, when you only have positive and negative as your options, we've got all the
Yeah.
infinite directions to go.
Okay.
But that's a cool observation. It definitely looks like a geometric series.
But it's not a geometric.
It's not a geometric series.
One stupid k.
One stupid k away from geometric. Absolutely. I completely agree with that. If I didn't have this here, geometric, because to move from one term to the next, I just multiply by negative 1 over 2 z minus I minus 1.
Okay, hear me out.
Okay, listening.
The modulus of any given number, if we just don't include the k, is going to be larger. And that series is probably going to converge.
True.
So like,
Well, for certain z.
for
right.
certain z, yeah. But then, so then if we added the k and made the modulus smaller, obviously the other series.
But how do we know we haven't gone to? Yeah, I gotta think about. Yeah. That I mean, yeah. So intuitively, this should
Intuitively,
converge.
It converges. Again, when we don't have less than with these sorts of numbers, it's not as clear.
True. The good news is it's actually even easier than that. So we can use either the ratio test or the root test to find the radius of convergence. So here's what we need to do to understand. And what is it to understand? To understand what values of z this converges for. And another way to ask that is, what is the disk of convergence? I'll spell it every way today.
It's English, it doesn't matter how you spell
Exactly, does it? Yeah, it doesn't. As long as it all sounds the same, then it doesn't matter. So to understand this, step 1 is identify the center. What is the center here? Careful.
1 plus I.
You gotta look at what's being subtracted off here, right? Because z minus c to the k, the center is the whole thing you're subtracting off. So our center here is, just like Lou said, it's 1 plus I. Yeah, check that out. I subtract this, it puts a negative in front of both of those. So here our center is 1 plus I. Cool. That's where the disk will be centered, for lack of another word to say that. Step 2 is find the radius of convergence. So this is r equals the radius. How far can I move away from that center in any direction and still have convergence? And the way to do this is as follows. So we have 2 routes. Sometimes one works better than the other, and I'll give you some tips on that. Use either r inverse, so that's 1 over r, equals the limit, as n goes to infinity of the ratio of a sub n plus 1 over a sub n. And this is the coefficient on the n plus first term. This is the coefficient on the nth term. And we'll do that up here so you understand what I'm saying. Or you get the same answer, but sometimes this is just, sometimes one is easier than the other, and sometimes this one is really painful. If you choose, this is your bread and butter. This is for occasional snacking, right here. So this is the nth root of the modulus of a sub n. Yeah.
Yeah, I was wondering, I was reading the book and I was wondering when will that ever be helpful?
Yeah, I'll show you when it might be helpful. You can always get by with this if you know
Lopital.
and especially like things like that. If you know a limit like that, or can find that using logarithmic limit techniques, if you know that's one.
Really?
I'm pretty sure. Well, let's see. Because part of this is reviewing how this all works and pulling things together. Let's take a look. Now you've got me wondering though. So let's let y equal the limit as n goes to infinity of n to the 1 over n. And I'm going to take the logarithm of both sides. This is all real stuff here. Taking the logarithm of the limit is the limit of the logarithm. Hopefully believe me. And this is actually true because log is a continuous function where it exists. That's when you can bring the limit in and out, when you have a continuous function. This is limit as n goes to infinity. Bring the 1 over n out in front. So really I've got this now. ln of n over n. Top goes to infinity, bottom goes to infinity. Seems like the top goes slower. I mean, it definitely does. Because here's 1 over n, or here's n, and then log n looks like this. So log n is getting flat as you move out that way. And so I expect that this thing is drastically smaller than this when n is really big. But I've got to L'Hopital it to see. So to take this limit, I use L'Hopital's rule. That's an LH there. Derivative of the top is 1 over n, derivative of the bottom is 1, limit of that is 0. So the log of the limit is 0. So what is y? It's 1.
Wow.
Good review, right? It's probably been a while since we've done this. Ancient memories.
Calc 2. Like
Calc
my
2 echoes
second
of the
year,
past.
second
Yeah,
year.
long time ago. Another lifetime ago.
Way back.
Way back.
I
Way
knew
back.
you were gonna say that.
Damn it, Lavina.
Way back at the dawn of time. So that was fun. So if you know things like that, or you feel like doing this occasionally, you can always do that. Occasionally. But there's certain circumstances when this is just like so sweet, it's just, you can't pass it up. So, then, step 3 is the disk of convergence. There's the, disk of convergence. Is this disk. It's the set of all z minus c less than r. If R inverse is infinity, so there's a couple cases here, so watch out. Warning. Does anybody even know like Lost in Space? It was a movie. It was like a black and white TV show for.
Then
Joey from Friends.
Yeah, I'm moving on. yeah, Joey from Friends. Yeah. Does anybody know him? Well, he used to talk about this a lot. So watch out. If our inverse turns out to be infinity, then that basically implies our inverse, or R is 0. And your radius of convergence is 0, and that means you only converge at the center. We only converge at the center. Just a single point, at the single point where everything's dead. Everything's 0. You can't move away at all without having the series. Oh my God, that clock isn't set back. Okay, it's like it's been a while.
you're good, Dr.
We've been here a
You're
while.
good.
I know I'm having fun, but so that's the disk of convergence, and that's the thing you need to find a lot in here, and we will be finding that for the rest of the semester. So let's do it for that problem up there. So in that problem up there, in the problem at hand, a sub n is the coefficient -1 to the n. I'm using n's here, kn, who cares? 2 to the n. Notice I'm not including the z minus whatever part. This a sub n is the constant part of the series. So limit as n goes to infinity. I'm going to write this formula a little differently because it's how you're going to want to write it. So this is limit as n goes to infinity modulus or absolute value. This is just a real number, so it's absolute value, but it could be complex, you don't know, is a sub n plus 1 times 1 over a sub n. This is probably what you want to do, because this is probably a fraction, and it's easy to take the reciprocal and multiply. So here, that's lim as n goes to infinity of the n plus first term is just replace every n with an n plus 1. And then over here, the reciprocal, so it's n times 2 to the n over negative n, -1 to the n. And then cancel, I'll let you, can you finish this up, please? I gotta eat more candy. I'm dying.
In that last modulus is on the bottom, is it n plus 1 times 2 to the n plus
Yes,
1?
ma'am. 2 to the n plus 1, yes. I sure hope we're recording. Oh, yeah. Positive. No, it has, well, so that's modulus, so be careful.
Oh,
Yeah. So the alternation actually evaporates.
yeah.
Notice that the -1 to whatever power is just 1 when you take the absolute value. So these two go away, they're irrelevant. Alternation in here will not matter. I've got a power of n for the 2 here, 1 more in the bottom, so a net 1/2 from the 2's. then what's left to actually take a limit of is this. And I can L'Hopital that, or I can realize that when n is really big, they're the same. What were you gonna say, Noah?
Oh, I was gonna say missing 1/2, but you pulled it to the front.
I thanks. I appreciate you keeping an eye on me. I need supervision. So, what is the limit?
You're much better than Hugo.
I hope I'm better.
Well, no, he will just. I'm specifically with equations. He cannot copy down equations correctly to save his life, and so he'll mess up on a bunch of things and be like, "I'm bad at math." And it's like, you set up everything up correct. You just missed like 3 numbers between the top and the bottom somewhere.
It's literally the only area of my life where I care about details and can notice them even. It's like the only thing I can keep organized in my whole life is math.
I feel that.
Yeah.
I think a lot of mathematicians do.
You think so?
Yeah.
Yeah. I think I'm the only one in our department though. Everybody else is pretty tidy.
See,
You think not? This is
yeah,
interesting.
no, definitely not. Sometimes, like, so it's Cyber's giant pile of scratch paper that really gets me.
Yeah.
Anytime I go in, he's just like, why not got a whole stack of scratch paper? And you grab this is a pile like it's this big. Of just
But it's a single pile.
it is.
How many of those do I have in my office? My whole office is scrap paper
Scrap paper and toys.
and
What is
hot
it called?
sauce.
I don't
And
know. I've been
hot
in your
sauce.
office.
All in like this far apart from each other.
What type of hot sauce?
It's actually the Taco Bell fire sauce.
That's a good choice.
Thank you. I really love I love Taco Bell.
Can't say the same.
My wife thinks I'm insane. She won't eat it with me, so I have to secretly pick up Taco Bell and eat it in like a parking lot.
Just get it for lunch. You don't have lunch together, presumably, unless she secretly works here.
No. Wait, what? What was the first part?
You can get it for lunch if you don't eat lunch together because you both have jobs.
You're right. I mean, I'm making much more of this than I haven't eaten Taco Bell in a year or so anyway.
Oh.
So.
Not a Taco Bell enjoyer.
You won't see me like under a bush somewhere. Is that Dr. T with all those burrito wrappers? Radius is 2. Because remember what you're finding is 1 over r with this. So r is 2. We have our center. We're done. This series converges. So our disk.
Absolutely.
Of convergence is the set of all z minus, I like putting this like this so it's really obvious what that center is, less than 2. Let's draw it, because we can. It's much more interesting than drawing it in, there's your center, 1 plus I, and then that extends, on up to 3i, and over to 3, and over to -2, and down to -2. And that's a fuzzy edge. So let's talk about that for a minute, because I haven't actually addressed that. Oh, you were, Sydney, what are you
I'm
showing?
just in a circle.
Oh. So in Calc 2, the next step, what you would find in Calc 2 was the interval of convergence. You would find the center, and then you would go C plus R, and you would have this edge out here, and then you would have this other edge this way, so this would be C minus R. And then we would make those soft, open edges, and then we would test the endpoints. So you would come in here and you would go, well, what if Z equals C plus R? And what if Z equals C minus R? Does the series still converge? That was a manageable task because there was 2 things to check. How many are there here on the boundary? Infinite. So we don't mess with that.
Absolutely.
We don't mess with that. There's some of these it will converge for, some of them it won't.
Is there any rhyme or reason?
Not that I can think of off the top of my head. But actually, it may be an interesting like research question for like just a talk or something.
Wow. When I give a talk, I'll let you know.
Thanks.
It's not gonna happen for a while.
Yeah, not for a while, but one day. I mean, it's an interesting question.
Yeah.
So, my friends, that's like it about Power Series. Let me give you one. Before Wednesday, please review the Taylor's theorem. Go through that section. I'm sorry, what was that?
I was gonna say that 6-3 or something.
Yeah, it's something like, yeah, that sounds right.
6-2.
6-2. So just please kind of refresh your memory, and we will talk about it again in the same way that we did this stuff. But I want to hit that on Wednesday. Let me give you a problem to do. Oh, well, let's just freaking make one up.
Oh dear.
Oh, yeah.
Rubino, you gonna be okay?
Huh?
You sound like you panicked a little bit.
I mean,
No? You're not panicking?
I did.
You want to say that with like more confidence?
did I ever say anything with full confidence?
Nope. And you do not.
You did say, I'm a rock with great confidence.
That,
Sorry, did I miss that?
yes.
Damn it.
What's the other way I could spell this? Is there any other?
I'm pretty sure we've gone through all of them, which is
I
really
know.
unfortunate.
Can you go with like a CH?
Oh.
Dish.
BESCH.
Sure. It's like find their
Absolutely.
edition of their convergence and okay. So find edition of Von convergence.
What have we come to?
End of the semester. Okay, hold on. I'm just thinking this in my head. Fuck it, I'm gonna grab one. I almost made it. It seems like I've been failing with my F-bomb
Okay.
fast. Here we go. Sure, this looks pretty weird. Okay.
Okay.
Oh God, no. No. Okay.
What's
So
that one?
My fault.
K equals 0 to infinity, z minus 4 minus 3i to the kth over 5 to the 2k. So let's actually write out a couple of the terms, see what this thing looks like. Always do that to get a handle on it. So when k equals 0, I just get 1. And then when k equals 1, I've got z minus 4. And I'm watch this. I'm going to make a little move right now just so that I'm like identifying the series center. It's 4 plus 3i over 5 squared. And then the next term is going to be z minus 4 plus 3i squared over what power?
5 to the 6th. No, 5 to the 4.
So let's do the game and then call it a day. I didn't get that last assignment from you, did I? No. Okay. Good, I didn't lose it.
Yeah, I could gaslight you into saying you did.
Well, that's, despite the madness of everything besides my math, I have actually never lost an assignment.
Really?
Yeah.
I am proud of you.
I thank you. I've had people try to convince me of that. And they were
That's
liars.
not nice.
They were liars. It isn't nice.
Yeah, it's been a bit of a hectic week with,
It's okay.
you know,
No worries.
things.
I hear you.
executive function disorders. So I gotta-
yeah, so forth and et cetera, yeah.
Yeah,
I
I
can
might try
relate.
to. I'm also gonna ask for an extension in another class where maybe we won't be able to get it, but that's fine.
We're good,
Yeah,
we're good.
cool. Again, it's mostly done.
I'm sure it is. I'm not worried. When you were,
I just there's a few more words that I need to
that's
define.
what I was thinking. You're like, I just got 4 or 5 more pages to do on this one problem.
Yeah.
I'm having it bound, and so it's at the printers right now.
No, what I really wanted to do was Knowles complained that I preserved paper like an 18th century, like a rare resource. And so what I really wanted to do was do all of my homework on like 2 note cards for him once. Like do it and then transcribe it. I didn't have the time because I have a life. But
Yeah, I was gonna say, if you're overwhelmed, that might not be a high priority.
no, it
Yeah.
wasn't, but
Yeah,
it
that's
would
good.
have been very fun.
It would have been. Man, I'm sorry. I think I stink today. I'm really sorry. I'm up here. I'm like, God, I stink.
Way far away from us.
Well, that's good. It's good. I was earlier. I was mingling with my freshmen, and I thought somebody stinks here. And I think I know who it was now.
That's crazy.
It wasn't any of the young ladies there. Yeah. I'm also a very clean person like that. I take like showers every day. I like even water. Whatever you say, Dr. T. This would be one where the root test would work really nicely. I'm going to use the root test because you're probably doing the ratio test.
Yes, I have done the ratio test.
What? Did you? I just had a feeling. I mean, this is the case when I would think, oh my God. Immediately. It's just, right? So when your coefficient is actually consists only of exponents, or it has exponents like this in it, this is a good thing to do. When every term has an exponent involving the index, root test is primo. So. And then, yes, exactly, so yeah, 1 over, so you gotta flip it, and then your disk of convergence. So, ooh, I like that 4 very much. Let's not draw it. Seems a bit silly. It's a circle of radius 25, centered at 4 plus 3.
It's a large circle.
It is quite large. So we could. I'm not doing that. Yes, ma'am.
So would most of them always be fuzzy circles?
Yes, they will all be fuzzy circles. And there will be points along the boundary that do converge and don't. So it's not of concern to us, actually.
We don't care.
We don't care.
I mean, you can check some of them if you want. Okay.
Really quick, what would this mean? If this turned out to be the case, what would that mean about R?
Oh wow. That's gonna be everywhere?
Yeah, R is infinite. So that might be a little note to make. That means it converges in the entire plane. Doesn't matter where you go. Fun. Thank you, friends. Always a pleasure.
Cool.
It's
Nice public admission of stinking on this thing.